Good morning. It is April 16th. Good morning. It 2021. April 16th. We are Inception broadcasting here for a moment. 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 We are Inception All right, broadcasting cleanly. Clean up the board up here. Today is actually class 636, but we are doing sorting and searching. There we go. All right. Good to see everyone broadcasting on YouTube. Double broadcasting for a moment in YouTube and in game. I'm going to shift out of game broadcasting. Just wanted to let you know that YouTube is going if there's any trouble. Going back to YouTube. And thank you, music. That is Thumper by a musician named Jim Hall. And that is open source music on the Free Sound Music Archive. All right, good morning. Good to see everyone here this morning. I'm looking around the classroom. Dodger's in class. That's great. Morning, Trent and Ethan. Good morning, Dee Dee. Good morning, Sam, Thomas, Josh. Good morning, Frank. Good morning, Matthew, over on this side. Morgan, Ben D, and Monty. Excuse me. Let's run through our checklist to make sure that we're all set up to go today. And for that, where's my checklist? Here we go. So I'm looking at it's the same checklist that we have over by the entrance to the auditorium, but I'm looking at a separate document to run through it right now. All right, so make sure you got your VPN activated in case you want to communicate on voice. I've got mine good to go. Find a quiet location and tell your roommates that you are in class and they're going to need to put away their timpani. Turn off your notifications on your phone and your computer so you're not distracted by questions from your parents about what an NFT is. I got do not disturb on there, and I got do not disturb on my phone. Good, set there. Open Canvas so you can see what's popping up today. Open up Eclipse so you can code along, although I don't think we're going to be using Saros today. Obviously, make sure you've got Firestorm up. That is helpful for being able to view content and to check in on the attendance machine in a moment. Rebake your avatar. So go under Avatar and Avatar Health and Rebake. Go under, make sure you're in the right time frame. So go under World and Environment and Midday. Sun should be set. Set your draw distance to a low enough number that you get decent performance. I'm at 224 this morning and doing well. Go to the classroom. If you hear me and you're not here, we're in the Granville Auditorium classroom. Make sure you can see your classmates' names so you know who's speaking and who's around in this unprecedented time. It's helpful to see that. Good morning, Addie. Check in at the attendance machine so I can get a record of your attendance. And if for some reason you're not able to work in Firestorm, I'd like to work that out with you, but I know some of you are traveling and whatnot, so make sure you leave a chat message in the YouTube broadcast so they know that you're here. Ben Fernberg, I see that you're here. Good morning. All right, great. So I'll take a second to see if anyone has any questions, and then what we'll do is we'll jump to the calendar. All right, and just keeping track of my windows here. Broadcasting on the screen right now, we have the Canvas calendar. It's not the right class. Let's put the right class up. This is the instructor view, so it might not be exactly what you've got. Today is April 16th. There's four short assessments for after lecture today. They're like, one question each. They're pretty lightweight after we go through our material. Hopefully we'll have a little bit of time left over that I can let you go to work on those. Two of them involve downloading code. In the Canvas, okay, so what else we have coming up? On Monday, we've got a second drone challenge assignment up. And let me see here. Sorry, Canvas. Sorry, Slack is tweeting at me, or whatever Slack does, it's sleeking at me. Let me pause notifications on that because apparently in my system, notifications did not pause Slack. Okay, so Monday we've got our second drone challenge assignment in today's Canvas module, which is class 36. Let me see if I can show that to you. Class 36 right here. There is a short video that will walk you through one possible way of sorting and searching places by distance. That's a helpful strategy to be able to use. It is similar to what we're talking about, or what we talked about last lecture, with how you sort an array list of arbitrary classes in whatever method of sorting you want. So for example, sorting COVID data by the number of cases, or alphabetically, or descending by number of cases, or ascending by number of cases. You know, when you have a given array list, you might want to sort it in all kinds of different ways, depending on the data that's in there. And the flexibility to do that is built into the Java programming language if you know how to do it. And we talked about 3 different ways to do it last class. The first way was to change the compare to method within a class. That's good if you are an implementer of a class. The second way was to write a comparator, and you can do that whether or not you control the class. And the third way was to pass a lambda expression to a sort algorithm so that the Java sort algorithm could use your lambda expression instead of the compare to method in a class. So this video will walk you through how you can possibly do that with your with an array list of places. And I believe I use a comparator in the video if I recall correctly. Okay, so that's class 36. That's what we're doing today. For assessments, drone challenge, you got a technique on sorting and searching coming up. After our second drone challenge assignment, I will update the code for the third one, and I'll let you know when that's ready to go. And then that'll be our last programming assignment before we have our final. And our final will be during the normal slot during finals week, and it will be online. It will be similar to our previous exams, except that it will be longer. And yeah, it'll cover everything we've covered in class. It'll be comprehensive. All right. Great. All right, questions or comments about logistics? Scanning my windows here. All right. Then, without further ado, let me get my Canvas window down. All right, last time, let me set up a little project workspace for today, although I'm not going to share it. I don't think that's necessary today. I'm just going to copy the previous one and paste it. Class 36, 416. Open that up so we can see what we're working on. And great. So the code you looked at last time did something along these lines. We had a main method that launched our program, as always. Notice it's a static method, so you can launch it without having to have an instance of the class that contains it. So you can launch main without having an instance of the analysis class. You just have to reference it. And the first thing that we did was we filled an array list. So an array list is a kind of data structure, of course, that keeps track of the order of elements that are in it. Not that it sorts it. It doesn't sort it. It just means that when you put something in that array list, it keeps its position in that array list, however the elements were put in. And as you search it and as you shuffle things around, the position of the different elements that are within it stay consistent. That's a different idea than sorting. The idea of sorting is to change the order in which the elements in the array list are being stored so that they are organized in some particular way. And that was the focus of the last class, is all the different ways in which you could reorder elements in an array list. Line 62 here demonstrates an array list that are filled with county objects. Now, county objects are not something that are built into Java. They're simply an object that I created over here, also in the project. You don't really have to know exactly what's in it, but I'm going to change this because it's driving me nuts, not countries, counties. We have some method that's going to get data and it's going to fill an array list. So we don't know much about get data just from this line of code. We just know that we know it's static because it's being italicized by Eclipse for us. We also know that it's going to return an array list of counties. So it's just a way to fill an array list. Then we're using the built-in sort method that comes with Java, part of the Java collections framework. It will sort our array list of counties in this way. Now, by default, what's going to happen here is it's going to use the county.compareTo method in order to decide whether or not or how two particular counties should be ordered. You might have Santa Barbara County, you might have San Diego County, and which one should come first depends on how you're sorting them. Are you sorting them alphabetically? Are you sorting them by population? Are you sorting them by the number of colleges or universities that are in them? All kinds of different ways you might want to sort a list of counties. Compare to is where Java looks to find how the implementer of county intended to have them sorted. And as someone who implements county, you can change that at will. And then when someone decides that they're going to sort counties, the sort algorithm uses compare to in order to do that. So what we're going to look at, and so this output here assumes that what's happening is that we're alphabetizing them, although that may or may not be true depending on how compare to is currently implemented. All of this is a black box, or at least line 64 is a black box. How does Java do the sorting of the counties? You don't know. And in fact, you don't really need to know, but you don't need to know in order to use it. But in order to be a good computer scientist, you do need to know how sorting happens. And the reason why you need to know how it happens is because it opens the door to the idea of algorithms and algorithmic complexity, and opens your toolbox, your analysis toolbox, to understand that there are different ways to accomplish the same task. Sorting is a really good one to start with. There are different ways to sort, and depending on which way you choose to sort, you might be waiting forever for the sort algorithm to finish, or you might be waiting a short amount of time for the sort algorithm to finish, even though both of them achieve the same output. So today what we're going to do is we're going to dig into the idea of how to implement that sort method. Not that you need to, because Java has done it for you, but because knowing how it works is an important knowledge to have as you are becoming a more sophisticated programmer. So what I want to do is I want to go through a selection of different ways of doing sorting and to talk about them and to use this as a segue into talking about algorithmic analysis, or what we call big O notation. Some of you might have seen a little bit of this if you did AP Computer Science. AP Computer Science touches on it a bit. And then when and if you take CS-120, we talk about it at greater depth in the context of more sophisticated and complex algorithms. One way that you could implement a sort algorithm is with selection sort. Selection sort is going to take an array list of elements and it is going to put it into an order. In this case, we'll talk about ascending order of integers. It does it in a particular way. There are probably, I don't know, I could probably name maybe half a dozen different algorithms for sorting off the top of my head. And they basically come in two different flavors, slow and the fastest we know about. It's possible there's some sorting algorithm that we don't know about that's even faster. That seems like a long shot given the amount of effort that's been put into trying to find faster ways to sort. But nevertheless, there are fast ways to do it and slow ways to do it. Understanding the fast ways requires understanding the slow ways first. So selection sort is one of the slower ways. So what selection sort does is it's going to rearrange the elements of a collection, and it's got to be a list basically in terms of collections, because sets don't keep track of order, and there are other kinds of collections that just don't make sense to sort. So we're going to store a list in a sorted order. We're going to rearrange the elements. And so selection sort is going to do this in a particular approach. And what it's going to do is it's going to look for the smallest element in the unsorted array. It's going to grab it and it's going to put it at the beginning of the unsorted portion. We're going to treat this, we're going to separate this particular collection as represented by the blue numbers down here at the bottom. We're going to separate it with the left half, which is going to be sorted, and the right half, which is going to be unsorted. And step by step, we're going to grab an element from the unsorted portion and move it to the sorted portion. So move it from right to left. So in order to do this, we're going to need to know how to write a loop that goes over our list. We're going to need to know how to swap elements in our list. And we're going to have to keep track of indices pretty carefully so that as we move through this array, we're not overwriting data or missing data. It's slow when we run it on large data sets for a particular reason, and we'll take a look at that. So let's look at sorting an array list of integers here. The way it's going to work is we're going to start with this particular array, 11, 9, 17, 5, and 12. And our first step is to do a complete sweep, a complete loop over this array, looking for the minimum element. Now, looking for the minimum element is one of those common array list algorithms that you should be comfortable with, and you're probably using it in the context of your drone world assignment. But as we go through this particular array list of elements, we're going to find the lowest element, and that turns out to be 5. And so what we're going to do is we're going to move it to the beginning of our array list. You can see that it's green there. I'm jumping back and forth between slides for this first move. So notice where the 5 is now. The 5 previously was second to last. And look where the 11 is now. 11's at the beginning. And what we're going to do is we're going to swap the 5 and 11. So now the 5 is at the beginning and the 11 is second to the last. We swap them. We know something now about our array. We know that array list. The very first element has the smallest element that was present in the entire array. And so we know that everything that includes the 5 and goes to the left is sorted from lowest to highest. Now it only has one element in it, so that's not saying very much. And we know that everything above the 5 in terms of indices is unsorted. So the next step, indicated by number 2 there, is we're going to find the next smallest element. So we're going to do a loop that starts at position 1, or where element 9 is. We're going to walk to the end of the array list, and we're going to find the minimum of that subset of the array list from 9 to 12. Turns out that 9 is the minimum element, and so we're going to swap that with the highest or with the lowest unsorted position. Turns out that the swapping doesn't entail doing a whole lot because 9's already in the right spot. So 9 stays where it is, and we move the boundary from what is sorted and unsorted, we move it 1 to the right. So now we know that this dark green element, the sort of tealish elements, everything to the left is sorted. 5, 9 sorted. Everything to the right we don't know about. We assume it's unsorted, and in fact when we look at the actual data, it is unsorted. So now our next step, bullet 3, kind of between 2 and 3, we searched 17, 11, and 12 for the smallest element in the unsorted portion. We identify it, and we swap it with the 17. So 11 and 17 get swapped. The reason we're swapping with 17 is because it's the lowest element of the unsorted portion of our array list. We swap it. And now we move our boundary 1 to the right. So 5, 9, 11 to the left of the 11, 17 boundary, everything is sorted. To the right of the 11, 17 boundary, everything is unknown, presumed unsorted. Now, stepping between 3 and 4, we continue and we search over the remaining unsorted portion for the lowest element, that's the 12. We swap it with the first index of the unsorted position, the 17. So 12 and 17 swap. We move the boundary to the right one, that's step 4. And now we know everything to the left of the 12, 17 boundary is sorted, 5, 9, 11, 12. And everything to the right we don't know, presumed unsorted. Now there's only one element left. And by virtue of having found everything smaller all along the way, we know that what remains has to be the highest element in our array list. And so there's actually not much work to do when you only have one element left. You just leave it there and move the boundary to the right. So finally, when you get down to step 5, everything is sorted. 5, 9, 11, 12, 17. In step 1, we had an array list. All the elements stayed in their position. In step 5, we still have an array list. All the elements stay in their position. But we shuffled them so that the positions that they're staying in are also the sorted order as well. Two different concepts that students have a hard time understanding. That maintaining an order in an array list does not mean that the order has to be a sorted order. All right, that's very important to get your head around. We're trying to get them in a sorted order. All right, so let's selection sort. Let's dig into the code a little bit to try and understand how this gets pulled off. Maybe another way of sort of thinking about this is thinking about just, okay, so let's use this picture of the Santas in the addition, and you're trying to sort them from shortest to tallest. What you're going to do is you're going to look for the shortest one that's in the line that remains, and you're going to call them into the addition. And then that is going to leave 3 Santas left over, and you'll find the shortest one of the 3, and then you'll call them into the addition. That'll leave 2 remaining. We'll call the shortest one into addition. There's only 1 left outside for our Santa Claus addition, and that necessarily has to be the tallest Santa Claus because we pulled everyone shorter out of the line. So if that helps you to get your head around what's happening with selection sort, that, good. That's sort of a different way of thinking about it, perhaps. All right, so here's some code that we can dig into. Let me see if I can make that a little bit bigger. My attempt to make it a little bit bigger did not help in that mechanism. Okay, so let me go back. Okay, I'm still there. That's fine. I'm not sure what happens if I zoom in. So can someone unmute on in-game and tell me if you see on YouTube that I have zoomed into the code? I'm not sure if the mechanism that I'm using to zoom in is going to get reflected by the recording software. And I can't see what you're typing, so someone will have to unmute to give me. Good. It's zoomed in? Okay, great. Okay, so here is our selection sorter class. Let me monkey around with it for a sec. Zoom down. All right, it's all kind of there. All right. Stabilize here. Okay, and actually, I want to go forward 1 slide. I prefer to kind of start at the high level and then dig into the details to try and understand what's happening. So here's the selection sort demo program. You can see that this is the main. This is where we have the main method. It's static. This is where we're going to launch our demo from. And the first thing that happens on line 11 is that we're going to fill an array with random numbers. We're going to take 20. We're going to fill 20 positions with numbers between 1 and 100. That's a method, a convenience method that we've got written in another chunk of code. Not so critical that we understand that, but I'll show it to you in a second. The main thing is that line 11 is just how we're getting an array, and it's random, so it's not like doing useful work the way we were doing with the COVID data, but it's to demonstrate what's happening. In line 12, we print out what's in the array when we start. In line 14, we sort it using a static method. You can see we're using a static method because we're using the class name selection sorter, calling the method there. So we don't need to instantiate an instance of selection sorter. We can use the method directly. We can't use any instance variables if we do that, but we can call the method directly. And then finally in line 16, we output the result. All right, so understanding this framework, line 11, we create some data. Line 12, we print it out. Line 14, we sort it. And line 16, we print it out to demonstrate that it's been sorted. That's our framework. So now what I want to do is to dig into line 14 by going back a slide in order to see what sorting is doing. All right, so I wish I could make that just window a little bit bigger, but alas, I can't. All right. This is our selection sorter code. Line 5 declares our class. You can see that 11 and 27, both methods have been declared as static. And so this is going to operate without access to instance variables, but can be used without creating an object. So our sort method is going to receive that array of integers that we created in the demo main class, main method. And this is where we do our selection sort work. All right, so what 13 is it's a loop that's going to start at the beginning index and go up to the last index, and the second to last index. And this is representing our boundary of what's been sorted and what hasn't been sorted. So this is representing the boundary between the teal and the light blue moving forward. For each position in our array, one at a time, starting at position 0, we're going to use our helper method down below, minimum position. Minimum position is going to take the array that we're busy sorting and it's going to take a position to start from, that's I, and it's going to look in every location I and higher to find the index of the smallest data element that's present in A, starting at position I and going higher. It's going to return the index of that lowest element. We don't know what the element is, but it's going to return the index. We're going to store that in min-pos in line 15. And then we're going to call a convenience method that we've written that will swap two elements in an array. So 16 is going to swap, and it's going to take an array that you want to swap things in. It's going to take one position that you want to swap with, one index, and it's going to take a second index that you want to swap with. So let's look at this for a minute and walk through it. So the first time we go through this loop, I will be equal to 0. And in line 15, we will ask for what is the position of the element that has the lowest value in array A, excuse me, starting at position 0 and going to the end. So what that means is the first time through the loop, we're going to find the absolute lowest value in this entire array, and we're going to get the position of it and store it in min-pos. We don't know what position that's going to be. That could be 0, meaning the lowest element is in the first position already, or it could be a.length minus 1, which means that the minimum position is at the very end of our array. We don't know what it's going to be, and so our algorithm has to work regardless of where that is. We grab it and we store it, and then we say, okay, line 16 is where we do the work of moving our boundary. We're going to move that lowest element to I. And the first time through our array, that means we're going to move it to position 0. If it's already in position, oh, what was that? If it's already in position 0, then the swapping does nothing. It keeps it where it is. But if it's in some other position, it's going to take what is currently in position 0 and move it into min-pos. After we complete line 16, we know that everything at index I and lower is sorted. And after we complete line 16, everything at index I plus 1 and greater is unknown and presumed unsorted. Now, the second time through our loop, I is equal to 1. And so in line 15, we ask for what the minimum value is, not in the entire array anymore, but in the array starting at position 1 and going to the end. We don't look at position 0 because in the first time through our loop, we already pulled out the lowest element. So now we're asking for the second lowest element. We're looking for the Santa that's still left in the audition line, not the Santas that have already been called in. Second time through the loop, line 15, we get the position of the second lowest element in our array, and we store that in min-pos. Line 16, we take the second smallest element in our list, located at min-pos, and we swap it with index 1. Boom. So after line 16, in the second iteration through our loop, elements 0 and 1 have been sorted. Elements 2 and greater have not been sorted, presumed unsorted. The third time through our loop, we ask for the minimum element from position 2 and greater. Line 16, we move it into index 2. So after line 16, 0, 1, and 2 are sorted. Next time through our loop, 0, 1, and 3 will be sorted. Next time through our loop, 0, 1, and 4 will be sorted. We'll continue doing this process until we get up to the last value we're going to evaluate. The last value that we're going to evaluate is when I equals a.length minus 2. Do you see that in the loop? The last thing I is going to have a value of is a.length minus 2. That means that there are going to be 2 elements left in our array. Line 15 will say, what is the minimum value in the last 2 elements of our array? Store that in min-pos. We'll swap it out. So in the second to last position, we'll have the second highest value. And then we won't execute the loop the last time, when usually you'd say I equals a.length minus 1, because there's no point in doing that last iteration through the loop, because we know the last element must, by virtue of being the last thing left, be the tallest Santa in the audition line, or oops, we jumped again, or rather be the largest element that's in our array list at this point, okay? So that's the high level thing. Now let's take a look at what it means to do min position. So every time we go through this loop, we're trying to find the minimum position. So let's take a look at that for a second. I just need to monkey with my window so you can see the full method. There we go. All right, and my throat is scratchy today, so a little coffee to keep me going. All right, so a couple things about minimum position. This is a static method, so it can be called without an instance, but it's also private, which means that it is a method that is called as a helper method from other methods within our class. And so in particular, it is only called from the previous sort method. All right, so minimum position is a helper method. You can see that it takes in the array that we care about, and it takes in an index of from. That's our starting position. And you can see that what we're doing is one of the common array algorithms that we looked at when we were introducing the idea of arrays, and we looked a little bit when we were looking at loops. Again, coming back to sort of reinforcing the idea that when I introduced the idea of common algorithms, that they are in fact common and they become building blocks for other more complicated algorithms. So in this case, that common algorithm of finding the minimum element in an array becomes a building block for being able to sort our array. And we see that here in the helper method minimum position. To find the minimum element in an array, usually we would search through the entire array. We would keep track of the minimum position, and we would perhaps say in line 29, it actually starts as position 0. But because minimum position is not finding the absolute minimum position, it's only finding the minimum position from location from and greater, we're going to start with minimum position assumed to be at index from. And then we're going to look at all indexes greater than from to see if we made a mistake, to see if some other index should be kept track of as the index that holds the lowest element. I'm doing this thing here where I'm talking about the index and the data separately. So being aware of when you're working with the index of a position and when you're working with the data stored at that position, it's very important to keep those two things separate in your head. So 29 is an index. 30 is a loop that's going over the indices of our array, starting at one position higher than our assumption, going up to and including the last index in our array. We do that by saying I less than or equal to a dot length, because remember our arrays are 0 index, start at 0. Line 32 checks to see if we should update our minimum assumption. If our proposed new minimum, the data in A at position I, is less than the data stored at our currently assumed minimum position, A sub minimum position, in that case, we change our assumption and we say, oh, we have evidence now that shows that our minimum position should actually be position I. So we're going to update our assumed minimum position on line 32, and then we'll continue our loop until the very end. So by the time we get to 34, we've examined everything from position from up until the end of our array. We believe that the data stored at min position is the lowest of everything we've examined. Oop, window jump, don't know why it's doing that, I apologize. And then we return that minimum position, which is then used up here in line 15 to help support our sorting algorithm. All right, what I want to draw your attention to now, before we look at our utilities, just for benefit of understanding that, I want to point out here that if you look at sort on line 11 and you look at minimum position on line 27, minimum position is called on line 15. And so actually what we have in the sort method is a nested for loop, because there's a for loop on line 13, and there's also a for loop in minimum position, which is kind of hidden in line 15. That means every time we loop through 13, we have to do a loop on line 30. It's a loop within a loop. And that becomes important for understanding the speed of how long it takes for sort to go, how long it takes sort to execute. Line 13, it's a loop that goes through every single element in our array, basically. And line 30 goes almost every element through our array. On average, it's going to go through half of the elements in our array. So we have a nested loop that's going through quite a few elements in our array repeatedly. That's important to understanding the speed of this algorithm. So let's back out for a second and take a look at our helper method. All right, so this selection sort demo is our overall structure of our code. And array now is just a couple utilities that we're using here. You can see that, let me get it in place. All right, so you can see that we are using an instance variable, which is a Java util random element. You're kind of familiar with this maybe from Drone World. We create a brand new one that's going to have its own source of randomness. We store it in an instance variable called generator, and we just use that in our helper method random int array. Notice 8 is private, so no one gets to use that. No one gets to see that from outside the implementation. But when we called random int array in order to fill up our array with random numbers, our first parameter was how long we want it to be, and our second parameter was how high of a random number we should go for. So in 19, we allocate a new array of integers that is length long. In 20, we loop through that array, and in 22, we put a new random number into each position in our array. And finally, in line 25, we return that newly allocated and randomly filled array. So a real basic algorithm for filling in an array, something you should be very comfortable with. All right, and then below it, we have the swap method. Now this has a little bit of subtlety to it. Zoom in here. So what we want swap to do is to take an array A and to exchange the value at index I and the value at index J. On line 36, we store what's currently at index I, and that's important because in line 37, when we move the data from position J to position I, we overwrite what is in position I. And if in line 36 we hadn't kept track of the data in temp, we would have lost it forever and ever and ever and ever. Fortunately, we kept track of it in line 36. So in line 38, we can replace the data that was at position J with the data we stored in a local variable called temp. And as a result of this, we're able to swap two elements without accidentally losing the data. If we had simply said 37 AI equals AJ and 38 AJ equals AI, we would just have two copies of what was previously in AJ in our array, and we would have lost AI. All right, so then finally, when we run our entire demo algorithm here, we see this kind of output. So the first line is the array of 20 elements that was filled by our random int array utility method. We see we get numbers between 0 and 100, I think actually 0 and 99. 65, 46. This is a good demonstration of the fact that the numbers are placed in position and our array list is keeping their position solid, keeping it there, but it's not an ordered list. We then call selection sort, and we can see that it does the work of pulling the 2 out and putting it at the beginning, then pulls the 4 out, puts it at the beginning, 13. We actually have double 14s in this particular run, so one of the 14s was found and moved to the beginning, then the second 14 was found, all the way up until we get to the last element of our randomly filled array. So it did a pretty good job of sorting there. All right, details of the selection sort. Any questions about what I just described before we roll forward? Let me switch to game audio to answer questions. All right, no questions, so we're back in YouTube audio. And we're going to just review a couple thoughts on this. So why do we need the temp variable in the swap method? What would happen if we simply assigned AI to AJ and AJ to AI? Well, we can't drop the temp variable because if we did that, then AI and AJ would end up being the same value and we would have lost one of the values depending on the order in which we changed them. So that was critical. I tried to draw that out when I was looking at the code with you. What steps is our selection sort algorithm going to go through to sort the sequence 6, 5, 4, 3, 2, 1? Notice that's an array that is in reverse order of what we want. And so the first step that we're going to go through is we're going to scan the entire array to grab the 1, and we're going to swap it with the 6. The second step, we're going to scan the entire array starting at the 5, and we're going to find the 2, and we're going to swap it with the 5. The third step is we're going to go through all the elements starting with the 4. We're going to find the 3 and swap it with the 4. And then we're going to continue the rest of the way, but it's going to end up that the remaining elements were in sorted order, so no swapping needed to be done. We do go through the loops, but there's just no swapping that happens. So I just short-circuited the visualization of that between the second and third drawings there. All right, what would we do if we wanted to change the selection sort algorithm so that it sorts the elements in descending order rather than ascending order, so that we have the largest element at the beginning of each array? Well, what we could do is we could change our minimum position helper method and call it maximum position. And so instead of finding the minimum element, we could use that common array algorithm to find the maximum of the remaining elements and swap that instead. So let's take a quick look at where that would be. So we would need to change our minimum position here. Whoop, whoop, whoop. There we are. Line 27, we'd have to change this algorithm, and basically it would come down to line 30. We should change our variable numbers and our method names so that they reflect the new way we're using them. But basically the big change is line 32. Rather than saying if AI is less than A min position, we'd say if AI is greater than A min position. Of course, min position doesn't make sense anymore. We should call it max position, but it's just a name, and so it would work. We would just need to change the less than symbol. For those of you who are tracking right now, what Java does when it implements this is instead of on line 32 saying if AI is less than A min position, this is where it runs the compare to method. It says if AI dot compare to A min position is less than 0, then swap. So what it does is it just replaces this less than comparison on line 32 with the compare to method, and boom, suddenly you have complete control over how everything gets sorted. Okay. So now what I want to do is I want to help you get an intuition for how fast the selection sort algorithm runs. So I'm going to use the word profiling the selection sort algorithm. You might know the word profiling from like a police context, police profiling, or racial profiling. You might know it from like talking about a shadow, someone's profile and a shadow. The way it's used in a technical context, when we say profiling, that has a particular technical meaning. And that technical meaning means measuring the performance of an algorithm while it's running. So it's an empirical approach. Let's actually run the algorithm and let's actually take measurements of it. And that's called profiling. And so there's some kind of sophisticated tools actually that support profiling Java applications. And they're kind of cool. You geek out into them. It's a little bit advanced for what we need to do here. But what we're going to do is we're going to manually profile this algorithm. And what we want to do is we want to measure how much time this selection sort algorithm takes. We kind of want to exclude the amount of time it takes to load up our random array, and we want to exclude the amount of time it takes to like launch main, all the sort of overhead stuff. And what we really want to do is we just want to hone in on the actual sorting behavior, because that's the part that we're interested in studying the algorithm of. We don't care about how much time it takes to write to the console. We just care about that sort algorithm. So in order to do that, we're going to measure the time, the clock time, right before we make that call, and we're going to measure the clock time right after we make that call. And then we'll subtract the two values in order to figure out what the duration of time was, or what the delta of time was, how much time elapsed when we were running selection sort. To do that, we're going to create a class called stopwatch, and stopwatch is going to help us measure the execution time of the algorithm. And we're going to be able to start and stop and calculate the elapsed time. And we're going to use a method that comes built into Java called system.currentTimeMillis. System is a class that's provided by Java. You can see it's a static method because the currentTimeMillis does not need an instance of the system object. We're just calling it on the class itself. What it does, curiously, is it returns the number of milliseconds that have elapsed since January 1st, 1970. January 1st, 1970 is kind of a time that is called epoch, E-P-O-C-H, epoch, and it is a standard moment in time that a lot, maybe all computer systems use as sort of a base time, a time zero for things happening. And I'm not sure that anything significant happened there, but it's a little bit like, uh, the birth of Jesus or something, 0 AD. It's just a standard moment when we kind of all agree on for timekeeping that it's the point zero. And so how many milliseconds has elapsed since time zero, January 1st, 1970, midnight, UTC, Greenwich Mean Time, is a long. We can keep track of that in a long integer. So our stopwatch object, we're going to call it right before we start. We're going to call it right when we want it to end, and then we're going to call it to get the amount of time elapsed. So just a convenience method for us. Let's take a look at what this is going to look like. So let's scroll through here. So let's start with the instance variables. It's hard for me to both zoom in and scroll here. Maybe I can, no, let me see if I can, what I would like to be able to do is this. Nope, it's not going to let me. Okay, so we'll just go in and out and try not to make you motion sick in the context. Oh, sorry. All right, so our stopwatch class has 3 instance variables. It has a long, which is elapsed time. It has a long, which is start time, and it has a Boolean indicating whether the stopwatch is running or not. All 3 are private, so all of them are just part of the implementation and help us to create the illusion that we're running a stopwatch. Our constructor stopwatch takes no parameters and calls a helper method called reset. So let's start by looking at reset to see what our constructor does. All right, down in reset, you can see that we initialize our instance variables. We set elapsed time equal to 0. That makes sense. We set is running equal to false. We return. The constructor returns. Our instance variables are set. The stopwatch is doing nothing, waiting for someone to call our stopwatch. All right, how might they call us? Well, they might call start and they might call stop. When they call start, if the stopwatch is already running, we don't do anything. So if start gets called multiple times, the second and subsequent time don't matter. If it's the first time we've called start, we go ahead and set is running equal to true, and we initialize our start time. We grab our current time millis from our system timer, number of milliseconds since epoch, and we store it in our instance variable for future reference. Because later on, when a user calls stop, if we weren't running already, if we weren't running, we just returned. But if we were running, which kind of makes sense, you're supposed to hit start and stop in sequence, then we turn is running to off. We go ahead and grab the current time that the clock reads right now, store it in a local variable called end time, and then we store how much time was elapsed in our instance variable elapsed time by saying elapsed time is incremented by however much time passed in the last clicking of the buttons. So assume elapsed time is 0 for starters, and the amount of time that we start our elapsed time with is when our clock ended minus when our clock started. So if we started at 1 and we ended at 10, the amount of time that elapsed was 9. And if we do it multiple times, we'll add on to elapsed time. But in this case, we're not going to do it multiple times. And then finally, we just have a getter, get elapsed time, which is going to return our elapsed time. If we're currently running, it's going to update how much time has been running. So if we're running and we call get elapsed time over and over again, you'll see it increased. But if we're not running, then we're just going to return the time that had elapsed since the last stop. This is I feel like I'm over explaining this. It's just working like a stopwatch. You start and you stop and you ask how much time has passed. All right, so now when we run our selection sort algorithm, we're going to replace selection sort demo with selection sort timer to be able to evaluate this. And so, zoom in here. Our main method is going to enable us to look at how much time it takes to sort arrays of different sizes. So line 12, we create a scanner to get input from the user. Unfortunately, in this demo, we don't cleanly close it, so we should see in.close in this code as well, but that's missing. Bad Professor Patterson for not closing his scanner. Shame. Speaking of which, sorry I don't have Dodger report for you yet. He had a bat. We walked him in. My wife walked him in with me this morning when I came in, and he had a rough morning. Passed a couple Labradors and a Labrador and a Golden Retriever, and nearly lost it. So just like flipping out. My wife got very flustered by the whole thing because he's a strong dog. So anyway, no pictures of Dodger, but I owe you some. On line 13, we prompt the user to enter an array size. And in line 14, we capture what the user entered in as a local variable n. We assume it's going to be an integer. In line 18, we use our random int array helper method to create an array of length n with numbers between 0 and 100. In line 22, we create a stopwatch object. In line 24, we start our stopwatch. In 25, we run our sort algorithm. In 26, we stop our stopwatch. And in 28, we ask our stopwatch how much time has elapsed, and we output it to the console. Really nice little algorithm. So if we execute this and we choose a rather large number and we say enter the array size, and the user types in 50,000, we see that our elapsed time in this case is 13,321 milliseconds, or approximately 13 seconds. That's fine. That doesn't give us a lot of information about profiling, but this is profiling, but it doesn't give us a lot of helpful information about what selection sort is like. How does it behave? In order to do that, we need to look at several different array sizes to see how the size of the array causes the time to vary. This is like any science experiment that you might do. The independent variable is the array size, and the dependent variable is how much time has elapsed. And so we want to construct a graph where along the independent axis, or the x-axis, is size, and along the dependent axis, or the y-axis, is time that it elapsed. So we can study this phenomenon. Here's what you might get. And it's going to vary. What's going to happen is it's going to vary. Amount of time, the absolute amount of time that's going to elapse, the number of milliseconds, is going to vary depending on the speed of your computer. But what's interesting is that the shape of the curve doesn't vary. The shape of the curve is going to remain the same regardless of what the absolute value along the y-axis is. So if along the x-axis we have the size of our array in thousands, so 10,000, 20,000, 30,000, 40,000, and so on, and along the y-axis we have the time in seconds, although we're capturing milliseconds, you can see the different points plotted along here. And the troubling part about this graph is that if we double the size of our array, we go from, say, 20 to 40, the amount of time it takes to sort that array goes up more than twice as much. That's kind of a problem if you think about it. So to see this clearly, let's look at how long it takes to sort an array of size 30,000, about 5 seconds. Let's double the size of that array to 60,000. How long does it take to sort an array twice as big? Well, it takes 20 seconds. Well, that's kind of problematic. That means that as we increase the size of the array that we want to sort, the time it takes to sort it is going through the roof faster than it's growing. The time is growing faster than the size of the array. We deal with a lot of data these days. And if the time is growing faster than our data, pretty soon we're going to end up in a situation where we can't wait for the sorting to finish because we're trying to sort so much data. You know, just imagine you want to sort all the people in the United States. It's not a like crazy big number. I don't know, what are we at, like 400 or 500 million? The amount of time it might take to sort all the people in the United States by, I don't know, income, social security number, I don't know, something about when they were born, whatever it is, you're talking about some like significant waiting time now. And that's one of the concerns about selection sort. Let's see if we can dig into that a little bit. About how many seconds would it take to sort a data set of 80,000 values? Well, we could look at how long it takes to do 40,000 values, which is about, I don't know, about 9.5 seconds. So it would take about 4 times as long, or about 37 seconds in order to sort that. So twice as much data, 4 times as long. This is one of the things I'm going to ask you to do in your follow-up today, which reminds me I probably should give you some time to do that. The shape of that looks more like a parabola than a line. And this is, okay, so reminding myself that you have some follow-up work to do. What I'm going to do is I'm going to stop here, which is the point at which we mathematically evaluate the algorithm using big O notation. And that means that we really haven't gotten far enough for you to do all of those assignments today. All right, so let's see. Give me 1 second and let me change the timing on Canvas for when you have to have these things due, because you're not going to be able to, you don't have enough information to be able to solve them all. Okay. All right, so for sure you can't do 5. I think you can't do 4 either. Let me check. All right, well, we have 4, and let's check 3. I think 3 should be okay. Waiting for 3 to show up. Three's okay. All right, so you can do 3. All right, so 2 things to do then is follow up 1402, 1403. I'll clean up the module entry for today, but your to-do list should be accurate if you look at your to-do list. All right, so let's stop there for today. We'll pick up on Monday with our last lecture about sorting and searching, when we'll look at the mathematical evaluation of selection sort, and then we'll look at the faster version, which is a merge sort. Okay, any questions or comments from y'all? I'll switch to YouTube audio or to in-game audio. All right, I'm double broadcasting YouTube and in-game in order to shut down YouTube. So just as a reminder, it is April 16th, Friday. We are talking about sorting and searching. There is a little bit of work to be done today. 14-02 looks like a quiz on Canvas, and 14-03 Canvas will be updated with that in the modules momentarily. Okay, signing off. Goodbye, YouTube. Stand by. All right, goodbye from YouTube.